Hello everyone, my name is Barbara and I would like to welcome you all to our latest Novedge webinar episode. This week, organic surface modeling and reverse engineering with Cyborg3D. Cyborg3D is a new 3D modeling and reverse engineering product that combines organic surface modeling and traditional CAD modeling. It is a unique blend of subdivision surface modeling and NURBS-based CAD modeling. So with the ability to convert between formats using nPower software patent technology. And Cyborg3D also provides tools for reverse engineering scan meshes into CAD formats. And a little bit more about today's presenter. Gary Crocker is the CTO and founder of IntegrityWare and nPower software. He has over 25 years of experience in the CAD graphic industry, amongst many, many degrees. Before we get going, here's an overview of what we do at Novedge. Novedge is one of the largest online stores for design software. We offer a huge assortment of software solutions that cater to virtually every designer's needs. So put us to the test and find the software you need on our webpage at novedge.com. And before we get going, let me show you where you can find us on Facebook, Google+, Twitter. We have a great Novedge blog with a bunch of interesting interviews and stories for our community. And next week, we'll have a webinar on the benefits to the move to Inventor Professional. If you have to run away, we understand, but don't forget that our webinar is recorded, so you can rewatch it on our YouTube and Vimeo channel. Just search for Novedge. And now, without further ado, I'm going to let Gary take the mic and the screen and introduce you to a fantastic new product. Take it away, Gary.
Okay, hello. Okay, let me know when you can see my screen.
Here, yeah, we can sure see it.
Okay. Well, Dave Gill, our president, is actually going to do the first part of the presentation here, so I'll let him take over for a moment. So we're just going to give a little background on who we are what Cyborg3D is. We have a very popular product called Power Surfacing for SolidWorks, which has won several awards. At the most recent SolidWorks World events, we've won consecutively the gold medal for the best software product. So Cyborg3D is based on that product. However, it is a standalone product, so it runs by itself. And we can consider it kind of sort of a Swiss Army knife of 3D software because it's able to deal with organic models, NURBS models, scan meshes, SubD meshes. It's a powerful platform that integrates both of these types of modeling concepts. So it supports 3D translation, 3D design of both NURBS and SubD, 3D printing, reverse engineering, and rendering and animation. We've currently produced 3 products, released 3 products just this year on Cyborg3D. There's a CAD to print product which specializes in 3D printing of CAD models. There's a CAD to poly product which imports different CAD formats and tessellates those CAD models into mesh models. There's a SubD2CAD model which it does SubD design and conversion from SubD models into CAD formats. And then soon to come, we have a few products that we're pretty excited about. We have a scan to CAD product coming, which is reverse engineering product. And then we have a easy to render and easy to animate products that are based on the KeyShot, integration of the KeyShot technology from Luxion into our Cyborg3D environment through a partnership that we have with Luxion. So Cyborg3D supports organic freeform modeling through Subdivision Surface modeling. I assume most of you are familiar with that, but let's go back one. So it creates by default Class A surfaces or watertight solids using the Subdivision Surface modeling algorithm. And those models are very suitable for 3D printing because they're watertight. Probably the key technology we have is our patented conversion between SubD geometry and NURBS geometry. And that allows us to deal with those different formats and integrate them into a common environment. And because of that integration, we can constrain between SubD geometry and NURBS geometry, and also between SubD geometry in itself. So you can do multi-body modeling that combines a number of different forms together into a single body or element. And then we also allow the NURBS type commands like booleans and filleting and shelling and such, and trimming and sewing of surfaces. Along with standard SubD modeling, we support hard and soft creasing, but we also have a patented level of detail editing that allows you to edit the SubD at different levels within the model, so that, for instance, if you've got a handle that you want to put some detail on, put some grips on, you can put the handle in there, or you can edit that at a lower level of detail without disrupting the overall continuity of the shape. So it's a nice way to do detail without adding a lot of overhead in terms of geometry and still representing the nice shape. Then we can export the CAD geometry to standard CAD formats, also to 3D printing formats like STL, and to SubD formats like OBJ. Here's an example of a multi-body element done using our technology. So it combines some NURBS geometry in the base and in the chuck, and then some SubD geometry for the top part and then the handle part. And you can see how there's a smooth connection between each of these pieces of geometry. And this is something that a novel approach that we take that nobody else is doing. As far as our reverse engineering tools, we have some unique tools that we've designed for handling scan meshes and converting them into NURBS-based geometry. We have our patented shrink wrap technology, which will shrink down the geometry to match the original scan mesh. And then we also have some patented tools for filling holes and maintaining the curvature of the surface that they're on. So for instance, in the example, you see there a hole in a curved kind of oval shape, and we can patch over that, and yet as the patch is done, the surface continuity is maintained as if the hole was never there. One of our customers, Saber Racing, has been using this technology to build NASCAR race cars. So what they do is they start with a stock car, like the one on the lower left, the Corvette, and then they reverse engineer it using our tools, and they can reshape it, put a fin on the back, a spoiler, lower the body frame, and make it more aerodynamic and more race enabled. And so what they've been able to do with our product is take a process that used to take them 8 months down to 6 weeks, which has enabled them to do more work and branch out into different areas and such. So it's been highly successful for them. Okay, with that brief introduction, I'm going to turn the time over to Gary, who's going to show us a little bit about Cyborg3D.
All right, here's Cyborg3D, and we're going to start out, first of all, kind of looking at the CAD to poly and CAD to print products. We're going to import a step file. It originally came from Inventor, called the Inventor Suspension. It's a fairly famous part. You see it every once in a while. And so with this part, we're going to show you how to control the tessellation, which is one of our great strengths, our tessellation engine, and also how to output it and position it and so on for printing. And so here it is. So we've just done an import of this, and you can see right now it's come in at standing on its side. So one of the things we can do is go over in our build volume tool, and let's say we're going to set this up for printing. We can say fit objects to build volume, and we can change it from the Z-axis up to Y-axis up. And so that has sort of oriented it correctly, and we can fit it to the build volume. Now, once we have it in here, we could, in fact, grab pieces of it and place it on different pieces of the, let me accept that. So we could grab different pieces here and place them in different spots on the build volume. But let's take a look first at the tessellation engine. So I'm just going to grab this one object, and we're going to isolate it so we can take a closer look at it. And I can show the polygons in one of two ways. I can either show the graphical, oops, hit isolate again. I can either show the graphical polygons, and so you can see the polygonal mesh that we've created, but that's just a graphical representation in a very fast way. Or if you really want to see the actual polygons that we would output, for example, to an OBJ file, we can turn on this one. And you can see some kind of artifacting here. And what we can do is we can change our Z-depth scale to compensate for that. 0.2, and you can then, that just kind of changes the Z-depth scale. So when we pull the edges forward, we can't see that. Now what can we do with our tessellation? We have like a preset, tessellation presets that we have. And so you can use these to adjust your tessellation. Or you can use a direct editing of the values. For example, instead of 25 degrees, we could have, 10 degrees angle tolerance. Here, let's go back to 25 for a second. Now, when you're outputting an object for printing, you often want a specific accuracy. And so this model is about 100 millimeters in size. So when you're printing it, depending upon your printing depth, the printing accuracy of the particular printer you were using, you might, for example, say 0.1 millimeter. And so that would give you the accuracy. So now the polygons are going to be within 0.1 millimeter. Oops, I changed that. Or you might even go smaller, 0.01 millimeters, if you have a very high definition printer. Or if you wanted to render on. Yeah. So here you can see we have a very, very high accuracy on this. Probably, maybe even a little too much for your printer. But let's go back to low accuracy for a second and show you another very interesting option that we can do with our tessellation. Now, sometimes you want, you can see how these planar faces have long, skinny polygons, and sometimes that's very undesirable. So we have a setting here which really doesn't affect accuracy so much as the shape. So let's take a 1 millimeter maximum edge length and see what happens. Okay, you can see it's basically given us polygons that are 1 millimeter with their maximum edge length. And so that's often good if you have an application, a downstream application that requires that. For example, some of the radiosity and rendering engines prefer to have a tessellation of this sort. Now, remember we had preview polygons here. Right now we have it on all triangles. We can ask for it to produce quads when possible. So if I retessellate this and produce quads when possible, you can see we have quads. So now if I export this particular object or the whole object, then we will get into an OBJ file, then we'll get nice quads in these areas here. So that often is a very useful thing to do because quads are often better and easier to deal with. So that's the sort of the basics of sort of the SubD to CAD and SubD to Poly. So we can take this either that particular object or we can export the whole model. And we can say, for example, export selected to a stereolithography file for if we're doing printing, or to a wavefront object file if we are doing, for example, transferring it to some rendering engine or bring it into a program like 3ds Max or Modo. So you can accept that, and when we accept that, it writes out the OBJ file for that particular object. So that's kind of an overview of CAD to poly and CAD to print. It's a fairly simple program. The cool thing is that we can, we can see exactly what our tessellation looks like on the object, and very easy to adjust the tessellation on the whole object. The other cool thing is it's all multi-threaded. So when I grab this and say I have all these parts here, and I want to change the tessellation, that it actually does every single object in parallel, and this happens to be a 6-core processor. See, it's very quick. Let's go to medium accuracy. See, it doesn't take very long to tessellate a fairly good-sized assembly here. All right, now let's look a little bit at reverse engineering. Reverse engineering is kind of going the opposite direction. Instead of producing polygons from CAD data, we're going to produce CAD data from polygons. And there's several different sort of workflows for that. Let's first of all import a scanned model. This is a moose antler, and we're going to import it into a mesh object. And a mesh object is something that we can reverse engineer. Okay, so here we have it, and if you take a look at the edges, you can see this is definitely a scanned mesh of some sort with a lot of fine detail on it. So one of the options we have, which comes in our basic SubD2CAD product, is the ability to take this and convert it over to SubD and do this thing called quad wrapping. And so we can wrap quads around this object. And let's take a value of 1% and give it a try. So it's going to wrap, take a triangular mesh and wrap a bunch of quads around it. Okay, you can see the quads here. But that probably doesn't, you've lost some of the fidelity of your mesh in this case. If you want to keep more fidelity of your mesh, you can always go back over here in the history viewer and either edit or delete the previous object. Let's say we wanted to capture a little bit more of this detail in here. We would need a few more quads in this. So for example, this model has 130,000 faces in it, which is actually fairly small for a scanned mesh. So we're going to do this operation again, and this time we're going to go 0.5% and run the quad wrapping algorithm on it. Takes a little bit longer, but now you can see that we've captured some of this fine detail in here on the mesh, some of these veins. We can go a little bit finer, but it does take a little bit longer. So for a quick demo purpose, we're not going to do that. I've actually run this at 0.02 and 0.01, and you will basically can't tell the difference when you're looking at the quad wrap mesh versus when you're looking at the actual original scanned mesh. So, but now that we have it in a quad format, It is actually a SubD. So we could go in and edit this as a SubD, for example. You know, if we wanted to take and move some things around and so on, we could do that. Probably not a good idea to do it that way. If you wanted to move them around, you might want to use the soft selection, which gives you sort of a radial fall-off way to move things so that it will stay nicely shaped. So you basically have a SubD model here that you can do things with. One of the most important things that we can do with this is we can take this model and we can convert it to a CAD VREP. So this is what SubD2CAD is all about. This is the engine here that will take a SubD model and convert it to a CAD VREP. And we actually have an option on it to optimize it for the quad wrapping. So if you don't do this, you'll get the faces won't be quite as optimized. It assumes you have a good SubD normally, but if you know if you've just done a quad wrapping algorithm like this, it's probably a good idea to hit this. And so we're going to accept this and start producing a boundary representation model. And this is the VREP that it has produced. Now, because the quad wrapping doesn't necessarily line up all the polygons, you have some things like this, but this is a very nice, if you select it here, you'll see that this is a solid with one volume, about 5,000 faces. And so this can be exported to a CAD package, and you can do Boolean operations on it and that sort of thing, because it is a nice solid. And so this is sort of the automatic way of taking a scan mesh and producing basically a VREP that you can read in. Now now if we're going to kind of switch modes here, and we're going to look at doing the same process, but doing it using the same model here, but doing it slightly differently, doing it in a more manual fashion. And this will be the scan to CAD product that is yet to come out. But this will show you how to retopologize this object using our tools. So I have the scan mesh read in, and I can say new reverse engineering SubD model. So now I'm in SubD, but I'm in sort of reverse engineering mode, and I can take and create some quads on this object. And here I'm going to do it somewhat intelligently because I want the flow of the model to go along with I want the flow of this model to kind of work along with the mesh. So if I take this and down, okay, so I just pulled these edges off, and I can take those selected edges and I can say constrain, and it will snap them onto the mesh. I'll do that again. And I probably want to shrink them a little bit because we're coming in. Move some things here. Whoops, I forgot to constrain them. Let me constrain those vertices to the mesh. Now, you can work this all over the part, and you can get a mesh, which when you convert it will have a much cleaner looking NURB because you're controlling the flow of the edges. So that's one of the important things here, is that we can actually control the flow of the edges using this technique. So let's see how accurate we can get it. And you know, once you're in here, you can do all sorts of operations. Like, let's say you got this a little too long, and you wanted to use your SubD modeling insert loop operation to add a loop or so in there. You can do that. Okay, but one of the main operations, one of our patented cool things that we have is, let's go to subdivision mode for a second. We just go to straight subdivision mode. You can't really tell unless we turn off and on a few things here, but it's not really very conforming to the mesh, because these are the only points that are on it. So when it does a subdivision, it doesn't conform real well to the mesh. But that is sort of to be expected. But we have something to take care of that. And it's called the shrink wrap operation. Now, shrink wrap, what it is going to do is it's going to conform. Oops, do a very good job there. I might have dropped something on. Yes, I did. Okay, so let me cancel that operation a second. Let me grab these things, and so that's what happens when you occasionally when you get a thin model like this, you can't really tell whether you're on the front side or the back side. One of the things you can do is you can go up here and you can, in the document settings, you can adjust the reference mesh Z-scale as well. So it will kind of tell you, okay, that's on the back, and you can see it better there. So we're going to pull those forward. Actually, I probably should unconstrain them first. Let me unconstrain all those edges and pull them on the right side of the mesh, and then constrain them again. Okay, so now we're all on the, we're good in terms of being on the mesh. So when we go up to our shrink wrap algorithm, we can change the levels here, and you can see it's now starting to very nicely conform to the underlying scanned mesh. And so I'm going up to 3 levels of subdivision right now. It will take a second, but you can see it will, it snaps in nicely. You can see it's really getting the detail of the mesh into the object. We probably want to go a little bit finer. These are probably pretty big quads. And we might actually want to do something real quick here just to, well, I was just going to do a subdivide all just to make everything a little smaller. So now when we go over and we go down in the subdivision levels, it's going to get finer even faster. So if we do shrink wrap again here, see at 2 levels, it's getting pretty good. At 3 levels, it's going to be really tight to the mesh. I have to do a lot more work, but there you go. See, it's very tight to the mesh. And now we can take this model and we accept that. It sort of keeps the the mesh dropping information in there. And in fact, we can go from there, you know, if we're at the object level and editing, we can convert that to a boundary representation. Yep, I don't think it worked that time. I may have to try it again here. I think I actually crashed it there. So let's proceed on to the next part. So let's talk about, so you should get the basic idea of how to work with this and produce a BREP from a scan mesh. And so let's go on to the next phase and start talking about if you want to do your own subdivision modeling. So normally when people do subdivision, they do it one of two ways. The first way is they'll start with a box and then conform the box to the shape that they want. For example, you can take and grab objects here, grab the faces in the subdivision mode and extrude them, and we can control this, whether each face gets extruded individually or separately. We can control the sort of the angle, the twist angle, and also the number of subdivisions that occur. Okay, so once we have this, we talked earlier about the creasing, and we can grab a face, for example, and throw a crease on it. And what this has done here is now this is a flat planar face when it gets converted. So you can see this is a hard edge there. So for example, if you converted this now and take it over to the CAD model, you would be able to fill at that edge. So if we grab this one, and we're going to do a different operation, offset loop. And so we've offset the loop, and you notice when we've done that, it is sort of rounded the corner. And one of the basic principles of SubD modeling is that the closer the edges are, the sharper the corner. And it's, one good analogy that I've heard is it's like a soap bubble. And the more edges you have, the more attraction that soap bubble has to that edge. So that's one way to sort of give you detailed definition. Another way is to grab, let me grab all the edges here. I'm going to select all the edges. Try it again. Okay. So let's do something a little easier here. Okay, so if we grab the edges and we select the edges, try it again. We can change the creasing on them. So the weight, if we did 100% crease, which is up here, you can see it goes right directly to the end. So as we change the weight, it pulls towards the vertices, towards the edges. Once you get up to a fairly high one, you're probably going to want to add a subdivision in there so you can see it better. And if you go really high on it, you might even need 5 subdivisions to be able to see what the eventual shape is going to look like. So let's talk about how the SubD actually works for a second. What's happening in the subdivision world is that each face gets subdivided per subdivision level. So if we take this model and we go to 0 subdivisions, you can see it goes right back to the original shape. If we only use 1 subdivision, you see each time we do a subdivision, we get 4 times as many faces as we would previously. So, for example, the subdivide all operation shows you what would happen if you do more and more subdivisions. Now, let's take a look at a specific model. Now, the interesting thing here is that we're using Catmull-Clark subdivision, so we can pull in models from just about anywhere. So we're going to import a model from a detergent bottle model here, which is an OBJ file. product model. Here we go. Okay, so we've brought in this OBJ file, which is already sort of set up as a SubD. And we're going to take a look and see what it looks like. And you see it's not quite there yet. So we edit it. We can take these two faces here, and we can do the crease operation to make that happen. And this is a fully, editable SubD modeling environment. So we can do things like grab a couple of faces here. If we wanted to do drastic changes in topology, here I use the bridge operation to basically make a hole through it. It bridges those two faces, and I can change the number of edges on the bridge. And as a matter of fact, we can have created this one, the handle with the bridge operation as well. Sometimes it's useful to work in polygon mode, so you can see, okay, here's the original edges, and to see what's happening with it. So anytime you're in here, you can in the SubD modeling world, you can freely modify things and shape them. So let's take a look at soft selection here for a second. Soft selection allows us to make modifications at a lower level of detail. So let's go into level 2, and we're just going to pull a few edges out here. And make a little bit of a shape to put your thumb on there, so you can easily tip it upside down and dump it out. And now when we exit the level of detail, we go back to the base level, you can still see those modifications there. You might actually want to go to a little bit finer level of subdivision so you can see them better. Because what happens is that detail is embedded in a subdivision level. So if you have, like we were at 2 subdivisions, you go back to 2 subdivisions, you can actually see the exact level that we were working on. So the cool thing here is that we can modify this object, and the level of detail on the handle stays where you would think it is. It's almost like adding detail onto the face. All right, let's take a look, and then we can take this, for example, now that we have the detail we want, we can convert it to a boundary representation model. Okay, here we have a boundary representation of that SubD, and we can export that. We can say File, Export, and save it to a STEP, SAT, or IGES file, for example. And then you can bring it into your CAD system and do some detailing, maybe do an offset and fill at the edge there, that sort of thing. So that's sort of one workflow where you can go and you can create import an object and work with it. Let's now take a look at something fairly complicated. It's a golf club model, and this shows sort of the typical complicated workflow for designing something which is a combination of an analytic object and a SubD object. So, for example, we have 2 B-reps, which are actually created inside of OnShape. One is the handle for this this thing, and the shaft and the hosel, and the other is the face. Now, both the shaft and the face are things which are precisely designed inside a CAD system to have a certain characteristic. For example, there's a bulge on the face in both directions. You see there's a slight bulge in this direction as well as a slight bulge in this direction. And what that does is that's sort of they engineer that to have sort of the maximum effect and the maximum spring effect when you hit a golf ball. So you really don't want a flat face there at all. It wants to be slightly curved, which is not necessarily intuitive, but that's the way they design them. So, so this shape will be the same on pretty much all of the drivers. So then let's take a look and see how we might create the driver here. So I've already created a SubD for the body, and basically it's a fairly simple SubD. It started out as a box, and I added some loops to it and deleted one of the faces, and so now it's sort of this shaped face. And what I've done before you've seen it is that I've gone through and done some conforming so that the shape conforms to the image planes. So that's kind of work I've already done to set this up this far, and now I want to constrain this edge to the analytic face. So what we can do is we can go in this references menu and add VREP. And so we're going to add this boundary representation, which is just a single face, into the SubD as a reference object. So I know what I'm referencing. And I have these edges selected, so all I have to do is there's a thing constraining the selected edges and vertices to the closest reference surface edges. So when I click that, it now has constrained these SubD edges tangentially to the edge of that face that we've imported from a CAD product. Now we don't necessarily have to always do it tangentially. We can, for example, change the angle. Like we might want to say there wants to be a 30-degree angle here, and you can see it has moved back to a 30-degree angle. So you can control both the angle as well as the strength of the tangency here, or you can actually turn the tangency completely off. And for this case, we'll leave the tangency on because we're going to look at it later. Okay, I'm going to accept that. And now that we have this SubD object in good shape, let's take let's finish editing it here, and we're going to convert that to our boundary representation. And then we're also going to do what's called a trim and sew operation, which will combine that with this face. And so now we've produced, if you look down in the bar here, we have a solid with one volume and no open edges. I'm going to change the tessellation a little bit. Let's go up in the accuracy here. And so now we have this object kind of ready to go. We can then, just for time, because we're running out of time here, we have the hosel, which connects these two together. And if we edit this one, I'll just quickly show you how we did that. And we can add the reference. We're going to add this VREP as a reference. And then we're going to add this surface, the outer surface of this, as a reference. And when we go in here and select these edges, I'm going to put it in subdivision mode so you can see what's happening. We are going to constrain these edges to the face. And you can see that now that edge loop is on the face, and it's tangent just like the other case. And we can take this edge, and we can say constrain this one to the edges of that surface. And we take a look in the front view and turn the transparency on. you can see that we haven't done a very good job of hitting the hosel. So we're gonna grab a point here, and you can see in the background here, this is where the image plane says the hosel needs to be. So we're just going to drop that down a little bit and adjust it so that we get the shape of the hosel. To conform to the image plane. And you can do that all around the outside as well. And then when you're done, you can take and do, let's end editing here. We can do the same operation and combine these all together and produce a single solid. But we're pretty much getting out of time here. So I think it's now time to open it up to questions.
All right, thank you, Gary. I think, yeah, just, ask away. There's one question so far. Does it use multi-threading for conversions?
Yes.
All right.
It uses the threads for most of the conversion process. All
right, great. So that was the questions. I'm going to leave a couple of seconds if anybody else. Okay. Yeah, I think that's it. And I also want everybody to know that we have there's three different kind of Cyborg3D, right? There's Cyborg3D CAD to print, then the CAD to poly, right? Is it 3 products that we have? So yes, just take a look on our website. Yeah. Yes.
SubD2CAD is the other product,
and
which is most SubD Mode is in that product.
And yeah, this is great. It's very exciting. Then it's brand new, and there was certainly a need. So I hope everybody's happy that you finally are offering it. I know, a lot of people are asking. We're asking for it. Great. Oh. Okay. So if you don't have, I don't see any more questions. So I think I'm going to, okay, yes, that was it. I'm going to have to take the screen back, if you don't mind.
Okay.
And
no problem.
let me know if you see my slide. You should be able to see my slide. I want to, I want to thank everybody for attending. Thank you from the Novedge team. And also, here's where you can find this amazing new product. Novedge.com, we have plenty of brands. You can go to brands, select nPower, or just type in Cyborg3D and the different products will come up. And for information on the latest specials, new release, join the Novedge network on Facebook, Google+, or Twitter, or subscribe to the Novedge blog. And don't forget the next week webinar is about the benefits you get from the move to Inventor Professional. And to watch today's webinar or previous one, just head on over to Novedge YouTube or Vimeo channels. Our webinar playlist has webinars for every software taste. So I'm just, what's left is to thank Gary and David. Thank you for the great presentation, and looking forward to work with you again. And goodbye, everyone. Thank you for another great webinar.
Thank you.
Bye-bye. Bye.